Okay, thank you for the introduction. Thank you for the invitation. So as you said, I will be talking about object discovery, which is not really robotics, but I think it's a good problem. I think it's a good problem to look at. So it's essentially having as input a collection of image or a collection of 3D model and trying to figure out what consistent content you have in this collection, what similar content you have in this collection. And I think it's a good problem because it really forces us to focus on issues that we already discussed in the past talk, but that I think are core, especially if you want to do higher level reasoning about things. So for example, how do you represent objects? How do you represent your data? So the natural solution today is to say, okay, I will just have a deep feature to represent it, but this has some limitations, and we'll see other kind of representation. In particular, it's something that's not very interpretable, and to me, having representations that are very interpretable is an important issue. It's also something that naturally comes without supervision. You just have your collection as input, and you have to figure out what's interesting in this collection, and you have to figure out which kind of similarity you want to find. And so, of course, there are many approaches to object discovery. Today, I want to focus on one, which is analysis by synthesis. And I will start by explaining you why I think it's a good approach, or how I came to think about object discovery as an analysis by synthesis problem. And it was actually by starting on the synthesis side, so trying to synthesize 3D shapes. This was a work that was done by many people, but mainly 2 PhD students, Bob Wex and Theo Deprel, and collaborators at Adobe. So it's work that we were doing in 2017, 2018. And at this point, the main new fancy method to generate 3D shapes was point set gen. And the core idea of point set gen is pretty simple. It's you have some shape representation, and you just forward it to a multi-layer perceptron, and you get 3 by n output vector that you interpret as n 3D coordinates for your point cloud. So that generates your point cloud. And so your latent shape representation can come from different other part of your pipeline. It can be an input point cloud that has been processed, for example, by a point network, or it can come from an input image that has been processed by a CNN, and then what you are really doing is doing single view reconstruction. So this was very nice. This was basically one of the first methods to generate a 3D point cloud, but it had several issues. So the first one is that you generated a point cloud with a fixed number of points. So there was no natural way to change the architecture, to change the resolution, or to change the number of output points. Second, so you generated points that you were hoping that the points were on a surface, but there was actually nothing constraining the architecture to generate points that were representing something which really was a surface. And it was also pretty hard to interpret what was happening in the network. So what we did, so one of the ideas we had was to change a little bit the network architecture to have something that looks a bit different. That was, instead of just giving the shape representation to the network, we were also giving 2D coordinates of a point on a unit 2D square. So the input of the network was the concatenation of the latent shape representation and the XY coordinate of the point on the unit square. And then you forward the 2 of them through the network, and you get as output a 3D point. So the output of the network is now a 3D. And you can do that, of course, for any point in the 2D square. And essentially, what you will get is a bunch of points that you will train to represent your shape. What's cool with this architecture is that actually what you are doing is really deforming a surface. So you can do it point by point, but you can really compute the full surface. And if you think a bit more about it, what your network is learning is really a family of parametric deformations from the unit square to a surface. And so since the network is continuous, you actually have some kind of continuity, and you can transport things like meshes. So you can really learn the mesh of a surface, not only learn point, but learn a mesh. Of course, if you just have one thing like that, you are pretty limited because the deformation, so the MLP can encode a lot of deformations, but to represent a complex shape, it doesn't work that well. So what you have to do is to have several such networks, several such input unit square, and several networks that will generate a set of 3D surfaces that you can concatenate together to build a full shape, to build your full shape. And if you look at it from a mathematical point of view, what you are learning is an atlas. It's a set of local parameterizations of your shape. So now it makes more sense mathematically what the network is doing. Also intuitively, it looks like a papier-mâché. So it looks like taking pieces of paper and warping them around the 3D shape that you want to generate your full 3D shape. Now, if we forget about the surface for a second and just look at the 3D points, what you can do, so these points, you can sample them in your 2D unit square, but what you could also imagine doing is considering them as parameters of your network and also learning them, so allowing them to move in 2D or even in 3D space. And if you learn to do that, if you do that, something quite cool happen is that the different patches, the different set of points, they will move in such a way that they will start to reconstruct part of the objects. So if you learn such a network to reconstruct a collection of shapes, for example, a collection of airplanes, something like that will happen. So each patch, each network will specialize on a part of the object. And what you will learn in the middle are really parts of the object. So in a way, without any supervision, you will discover the parts of the object and implicitly also correspondences between the full shape collection, something that's not at all in the data, at least not at all in the data we use. And the key for that is that the deformation that the network in the middle, the MLP can do, you have to limit them. Otherwise, the patch could be warped in any way. And pushing it to the limit to really have good representation on good parts like that, what you can do is you can have, from the latent shape representation, have a multi-layer perceptron that predicts a very simple transformation, an affine transformation. So we work with affine transformation, and then basically what the full network can do is just compose the different parts that it has learned and compose them after an affine deformation. And that's how it can reconstruct the full 3D models and basically all the 3D models in your collection. So this is what the results look like. So on the left, you have two examples of shapes in our collection. And on the right, you have the reconstruction. And in the reconstruction, we highlighted 3 of the parts. And you can see that there are parts that make a lot of sense. So you have the engine, you have a wing, and you have the tail of the airplane. And basically, in each shape, you can really understand how the network played with the affine transformation to try to make it work. For example, you can look at the tail. It's pretty funny at how it's able to reverse the tail to explain a kind of a weird airplane shape. And also, independently of any reconstruction, you can also just look at the collection of elementary structures that you have learned, of these patches that you have learned. And so actually in the paper, we have 2 ways to learn them. So one just point clouds, the one I explained, and one which is more surface. And that's what you can maybe see on the animation below. But we can learn these parts also by deforming a surface and have parts that are really surfaces. So basically, essentially, just by trying to do better reconstruction, which was initially our goal, we come with this method that can analyze the 3D collection and directly discover things like parts in this collection of 3D model. And the objective here is really, really simple. It's just essentially an autoencoder. We are just trying to reconstruct the 3D shape. And by constraining the type of deformation that we can have, and by learning the elementary parts, maybe the prototype for the parts, we are able to discover this set of parts. So we try to push that further, and we try to go back and try to re-understand why it was working, or why it had this behavior, why it was finding this kind of parts. And so that's work that we did in the last 2 years, and that was mainly work done by Tom Monnier with several different collaborators. And so we took the approach we had, and we tried to really go back to the basics and not even do part discovery, but really go even back further and go to clustering. So the idea is the following. When you are doing clustering, for example, with a k-mean algorithm, what you are doing is essentially learning to reconstruct the data as well as you can from a set of prototypes. So it's basically analysis by synthesis that you do when you are doing k-means. So here we have a set of points, blue and green dots, and we have 2 prototypes that the k-mean is learning, which are the green and the blue cross. And if you have a new sample, for example, the xi here, to decide if it's associated to the left cluster or to the right cluster, you just compute the distance with the cluster center, and you associate it to the closest distance. And the loss that you are minimizing is just a reconstruction loss, is the one written below. So in the standard algorithm, you don't exactly look at it like that, but you can totally see that as something that you can train with a neural network where your parameters are only the centroids. So if you are thinking back on the 3D models, it will be, for example, the prototype of the parts. That's the analogy that you can make. Our idea is that now what we allowed was to transform these parts, to have some transformation on this part. For example, here in these simple 2D examples, we could say that we want to do clustering, but we want to allow rotation around the center. And if we want to allow rotation around the center, the two groups that we would like to find are the two groups that I show here of blue dot and green dot. And the two prototypes we learned, they will also be 2D points in this case. So the two crosses, the green cross, the blue cross. But now for a new point, when you want to decide in which cluster you want to associate it, you have to consider that you have to allow rotation. So you have to find the best rotation of the green cross and the blue cross, and only then compare distances with respect to the points that you are trying to associate to a cluster. So if you put that into an equation, you get the equation at the bottom, where the only difference with k-mean is that now we allow this transformation. And this transformation, of course, we learn it with a neural network. So I will try to wrap it up in terms of equations. So you start from a standard clustering, so a standard prototype-based clustering. So you are trying to learn centroids, C1 to CK, given an input data set, and the things that you are optimizing are the CK. The next step you can go is to say that you want to do transformation invariant clustering. So you will allow any transformation in some family of transformation, for example, rotations of affine transformation of your centroid, and you will minimize the same loss, but taking the best possible transformation every time. So that's another idea that's actually pretty old. The first ones to develop it were, I think, Frey and Jojic in the end of the 90s. And for them, the transformation was typically just swapping pixels, swapping different pixels. And you can see that this is actually pretty hard to optimize because every time you have to optimize for the best transformation to minimize this loss. And so, in fact, what we propose is instead to predict this transformation with a neural network. So F1 to Fk are neural networks that will predict the best transformation for a given sample of the different centroids. And now what we are learning are both the centroid and the deformation that you have to apply to them to explain the data. So it will look like something like that. So for a simple case, for the case of MNIST, you have an image as input, a sample that you are trying to reconstruct. And you have prototypes. So for example, you have the prototype CK is a 3 in this case. And what you need to do to try to reconstruct as well as you can the input is to predict a set of transformation to apply to this prototype so that it matches the sample. And so we have a network, the CNN, that's taking the sample as input and predicting different types of transformations that we apply to the prototypes. For example, here an affine transformation, a morphological transformation, and a TPS transformation. And everything we need is that these transformations need to be differentiable, and ideally we want to be able to control it. So have transformations that we really understand. Another easy transformation to add will be to add color transformation, adding just a constant color to the digits. So to summarize, the key idea of this deep transformation invariant clustering is to jointly optimize the clustering parameter and the transformation network, and to do it with SGD. There is, compared to k-means or just reconstruction, there is really no additional loss, no explicit regularization, just the network and the constraints on the deformation that we have. And the cool thing is that the clustering really happens in pixel space. So if you are looking at images, your prototypes are really images, and we compare distance between pixels, between real images. So we are not comparing distance between features. We don't have abstract features. We are really deforming images and comparing directly images. So that makes the process very, very interpretable. So here are some results. What you have on top are two examples of the prototype that you learn on two simple data sets, MNIST and Fashion MNIST, if you just apply Gaussian mixture model to them. And just below it, what you have are the same things, but for the transformation invariant, deep transformation invariant version of GMM. So I explained it for k-means, but you can also apply the same thing to GMM. And what you see is that the prototypes are much, much, much sharper. And that's associated to the fact that the clustering will work better quantitatively as well. And what the algorithm is really doing when it has an input image, it predicts transformation for all the prototypes. So if you have an input image in blue below, it predicts transformation for all the prototypes, and it compares them to the sample, and it just selects the best one, which is outlined in green for the 4 different examples here. And so quantitatively on this toy data set, it works very well. So I don't want you to really look at the different numbers in this table. That's the paper, so numbers are better or similar for us. The thing that's interesting is that we had a very, very hard time finding methods that were doing clustering in pixel space. Basically, it's essentially k-means and GMM. All the baseline, all the state-of-the-art baseline, they are rather learning feature and doing clustering in feature space. And typically, they are learning feature in kind of a complex way. Whereas I think what's interesting with our method is that we really have pixels. And that makes things very interpretable, and that actually makes the algorithm work on real data. So these are results with real data. Our input data set here is just a collection of images of Florence that comes from a 3D reconstruction data set. So it's not especially designed for clustering. And what I show you here is on the top row, it's how the prototypes look like. And on the bottom row, you have on the left a sample image from the cluster associated to the prototype. And on the right, the reconstruction that we get by doing our color and affine transformations, essentially. And so what you can see is that the different prototypes, first, we can interpret with them very, very well. And they really correspond to the content of the cluster, which will really not work at all if you are doing k-means or something like that, and which you could not look at if you had just features to represent the cluster. And the second thing is that we can do reconstruction very well. So with a single prototype, we can reconstruct quite different looking images. Of course, it doesn't always work. So it's a data set where there are also just random views or views that are seen in very few times. And so in this case, of course, you have clusters that are prototypes that don't really represent anything, that are just used to represent very different things. But the majority of the cluster and the prototypes are very interpretable. We went even further in terms of realism. We applied this idea to cluster Instagram images. So we just queried images on Instagram with a hashtag, so Santa photo here, for example. And if you do that, if you ever looked at Instagram hashtags, so it's never clean. There are a lot of different images. For example, somehow you have images of dogs or cars that have nothing to do with Santa. But if you apply your clustering to it, you can actually get cluster with centroids that make sense, which are the ones which are visualized below. And you can actually recognize different things. So, for example, the chair of Santa, or Santa with 2 kids near him, etc., etc. And we did it so for several different hashtags. So this was just clustering, and this was back on images. We can actually do the same thing for 3D model. We did the same thing for 3D model, but so with a single prototype, no parts, just different prototypes, just trying to represent a collection of 3D model by having affine transformation of different prototypes, and also to make the representation a bit richer, but keep it interpretable, we had an affine space, typically 1 or 5-dimensional affine space of 3D model associated to each prototype. And the cool thing when you do that is that you can represent databases that are actually kind of complicated. So if you know the ABC dataset, it's a huge dataset of lots of 3D models of mechanical parts. And it's a bit hard to know what's inside to understand what the different data are, what the different 3D shapes are. And what we get as output of our clustering is, so first the clustering of the different shapes, but also by the linear space, modes of variation of these different shapes. So you can actually visualize what are the different shapes you have in the data set, and the different kind of change that you can have. So this is just to show that this works much better than just doing k-mean clustering. This works better than just having an affine alignment, so adding some linear space real. And that's just the prototype that we get when we add one step after the other. So that was all now with a single object, with a single prototype. Let's try to go back to having several objects and a variable number of objects. So again, what we would like in this case will be to have a collection of images as input. For example, you have 2 data sets, 2 toy data sets on the left. And what we would like to have as output is prototypes that will represent all the individual objects in the data set, and ideally their segmentation, their color, etc. And how do we do that? Well, we have this model of image formation that's very simple. That's just a layered image formation model. So you have a background, and then on top of it, you had these prototypes, deformed prototypes that we call sprites by analogy with all the arcade games. And so you learn both the sprites and how they can be used to reconstruct the images with this kind of layered representation. And what I think is nice is that when you do that, you really have something that's completely interpretable. You have the different sprites, so you have some notion of objects, you have their position, their scale in images, and you have their color. So you actually have a lot of information about how the image was built. I don't really have time to go through the pipeline, but it's a bit the same as before. We start with a set of prototype or sprites that we learn. We have a background model as well for this image formation. We have an input sample that we try to reconstruct. So here, for example, 2 digits of an MNIST overlapping. And what we do is that we have a network that takes this sample as input and predict transformations of the different sprites. And then we compose all of them with the background in a specific order. And it gives us a set of resulting image. And basically, the reconstruction is the best possible reconstruction. So, and the things we are learning are with the sprites, the background model, potentially, and the deformations that we can apply, or the CNN that predicts the parameters of the deformation. And the rest is completely deterministic, interpretable. You have a few technical issues, in particular occlusion or selecting the good sprites without generating all the composition, but it works very well. So these are examples on a toy dataset, toy synthetic dataset, where we have to find the different shapes. So I already showed them to you, and so it works very well. It allows to do things like manipulation, image manipulation, because now you really have a decomposition of the image. So that's what's shown here. What's interesting is that it also works on real images. So these are datasets that are standard clustering datasets, but a bit harder, as they are actually real images of a house number. And you have, here I show you the clusters that we get with the DTI clustering without a background model, and below with a background model, where we really have the sprites that represent the object, and so the sprites are not tempted to represent the background. And so you have gained something. So first thing you have gained, another thing you have gained is also that you get segmentation with this sprite. We have sprites that are RGB plus alpha. So you can do co-segmentation, and we did it for a horse dataset, for example, and we learn to reconstruct these images, and we get the segmentation completely for free without any annotation. We can, of course, do it as well for the images I showed you before, the images from Instagram. And so I didn't emphasize it a lot, but it works if you have several objects in the scene. So in this thing, typically you have a single object of interest, but it works with several objects. You saw it on the different toy data sets. So what I like in this approach is that it's really a very, very simple framework. It's really just learning reconstruction. It's pretty close to k-means. You can really go back to this very simple basic k-mean algorithm. It works great in practice on all these toy data set and also on real data. Doing clustering on real data is actually pretty complicated. And the key idea is really just to have this analysis by synthesis, but constraining the type of deformation that you can. And the last thing is that you have something that's very interpretable, and I think that will be crucial in particular for reasoning. So before finishing the talk, I would like to just highlight a few related things. So the first thing is that I didn't talk a lot about the relation to robotics, but I think actually this analysis by synthesis framework can be applied to robotics, and this is an example of a work that was done by Yann Labbé, and it was a work with Joseph Civich. I think he might have presented it this morning. So here it's really a robotic application, and you want to do 6D pose estimation of objects, either a set of objects in a complicated setup with multiple views, or a complex object, for example, a robot which has articulation, etc. And so what we developed for this problem was an approach that in robotic, in pose estimation, people tend to call more render and compare, but to me, render and compare is pretty much the same thing as analysis by synthesis. So you have some prediction of what the state of your scene is, you render your scene, and you compare it with the actual scene, and from that you predict update or you predict changes. In this case, to the 3D pose of object. But I think you have the same logic of trying to generate the scene, comparing what you generate with the reality, and trying to make a better generation of the model. And so this works extremely well for object pose estimation and robot pose estimation. Another thing I wanted to mention is that, so I talked a lot about this analysis by synthesis approach. Of course, it's not the only approach to object discovery. I think another approach that's very interesting is working with correspondences. And so that's a work that was done by Fishen, and that's on arXiv. And the idea is that you will train a network to have two images input and predict co-segmentation mask and correspondences. And from that, you can build a graph of correspondences and do object discovery. And you can do, actually, we showed that you can do object discovery on very different scenes just by training with completely synthetic data. So we trained the network to do this co-segmentation and correspondences just from synthetic data, very simple synthetic data. And then we show object discovery on the internet dataset, which is the one at the bottom right, and on a painting dataset that looks pretty different. And we even showed that this can help for geolocalization, which is again a very, very different problem. So I think correspondences are another way to go and are also interesting to try to solve this problem. And I think what will be great will be to mix the two. And it's a bit what we did in this work, which is not an archive, but will be an archive very soon, which was done by François Darmon. And in this case, so it's a work about 3D reconstruction. So we have a set of images of a 3D scene, and we learn the 3D scene with kind of a NERF type of approach. So this is more like analysis by synthesis. You have a model of the scene that you're optimizing to optimize the rendered image. So you can also see that as analysis by synthesis. And so that's a pretty standard approach right now for multi-view multi-view reconstruction. And what we added to that was also with the same model, with the same implicit occupancy model, to actually have explicit correspondences between the different images and actually deform patch from one image to the other and adding a correspondence kind of score. And if you do that, you really gain a lot compared to just the normal implicit 3D scene optimization in terms of accuracy and in terms of completeness of your model. When you add this kind of correspondence cost, you learn a much better model. So I think this idea of mixing kind of analysis by synthesis approach or implicit object model or scene model and correspondences is something that we should also look at, and that can be interesting. Thank you for your attention.